Hi, welcome to Introduction to Aerodynamic Objects Tutorial 3, my first wing. And in this tutorial we're going to make a wing that generates lift and understand the importance of angle of attack. And in this tutorial we're going to make a wing-like aerodynamic object that produces lift. Then we're going to see how the lift varies by changing the pitch angle of the wing, the elevation and azimuth angle of the wind, and then by flap deflection. And the really important outcome is that we understand the concept of angle of attack and how lift depends on it within aerodynamic objects. So this is our scene diagram, and over here we have our wing. We've got our wind vector coming in here and our drag as before, which is parallel with the wind. But we've got a new force here, lift, in green arrow, and that acts perpendicular to the wind. And the really crucial thing here is that the lift depends on the angle between the wind vector and the plane of the wing, and that angle is called angle of attack. So over here we have our aerodynamic object that we're creating. At the top we have our rigid body. Next down we define our shape. Next down we define our flow physics or our aerodynamics. We have a drag model, but this time we now have a lift model. And also on this object we've added a control surface component and some graphics to visualize that surface. So here we are in Unity, and I've saved this as tutorial 3 work in progress. And let's start by adding some wind to our scene. So right click, aerodynamic objects, flow primitives, uniform flow, same as we've done before. Let's add some field visualization arrows. So flow visualization, field arrows, and I'm going to make the box 10 by 10 by 10, and I'm going to reduce that radius to 0 to get it out of the way, and I'm going to change the number of arrows to 2 by 2 by 2 just so it's less cluttered. Let's just test that before we do anything else. Okay, that's what we wanted. Flow field arrows in a box, uniform flow. Great. Let's make our aerodynamic object. So I'm going to do right click, create empty, and I'm going to call this wing, and I'm going to add a rigid body. Because we're going to do this test with it kind of fixed in space, I'm going to click is kinematic on here, so this basically fixes it in space. Next up, let's make some geometry. So I'm going to start off with a 3D object, a cube, and essentially we're going to kind of sculpt a wing out of this cube. And just referring back to our conventions for aerodynamic objects, our assumption is that the blue arrow is forward, the red arrow is to the right, and this is to help us orientate things and make things the right way around when they come in. Aerodynamic objects doesn't care which way around anything is, it'll calculate the answer for you. This is really for human beings so that they do things so that they're consistent. We're going to make our wing so that we assume that the flow is going to be blowing from the z-axis, the blue axis, and so we need the span of our wing to be in the x direction. So what I'm going to do is stretch that out to 6 meters. So we made a bit of a brick there, so it's looking a bit wing-like, but I think that would just be more drag than anything else. So what we need to do is make it a bit thinner, so it's more like a wing. So what I'm going to do is change it so it's 5 centimeters thick. Okay, let's add some aerodynamics. So I'm going to do create empty and call this aerodynamics. We're going to, as before, add our aero object. And we're going to add a drag model, but also this time we're going to add a lift model. We need to connect up our rigid body. And the other thing is, since this is a rectangular shape, let's change the reference area shape to rectangle. Okay, so this would actually do something if we press play. It would generate some forces, but we wouldn't be able to see what they are. So what we're going to do before that is add some visualization components. So let's add a drag arrow and a lift arrow and a wind arrow. Okay, so let's just check what we've done. We've got a wing, it's got a rigid body on it, we've got a cube, so this is our geometry. I'll just rename it geometry so we know what we're doing. And we've got our aerodynamics there. We've got a drag model, a lift model, we've got drag, lift and wind visualization arrows. Okay, let's give this a go. Okay, so we've played it, we press play, but kind of nothing is happening in that we've got wind blowing on our wing, but there's a little bit of drag there. If we go up to our uniform flow, there's a bit of drag but no lift. So if I increase the speed, we can see the drag goes up, but it's not producing any lift. And the reason is because we haven't got any angle of attack in there. The wind is coming straight in parallel with the plane of the wing, so it's just producing drag and it's not producing lift. So if I set that back to 1, what we need to do then is change the angle of the wing relative to the wind, and we do that first off by changing the angle of the wing relative to the surroundings. And looking on this, we know our x-axis is the one in the axis of the wing, so what I can do here is vary the angle of this. So I'm now increasing the angle of that. We can see a magic green arrow coming up, so now we're reducing lift, more and more lift, come out a bit more lift, and then reaches a maximum and then starts coming down again. And what we saw there was that as you increase the angle, the lift goes up, but eventually you reach a stall, at which point the flow changes behavior over the wing and the lift drops off. And as we're going further up, the lift is now coming down, so we're getting less and less lift, but the drag is going up. And often when you stall a wing, the thing that's most concerning is not necessarily the loss of lift, it's the massive increase of drag. And if we go all the way to around 90 degrees angle of attack, we see that we've got no lift and lots of drag. And carry on round. So aerodynamics doesn't really care which way up things are, so now this wing is upside down and we are producing lift in the downwards direction. So if we're doing a loop-the-loop, this might be the top bit of the loop-the-loop, and we're actually producing lift downwards, and that's absolutely fine. Reset that. Okay, so what else can we do? That's changing the orientation of the wing. Let's change the orientation of the wind. So if we go up to our uniform flow, if we now change the elevation of the wind, so now the wind is coming from underneath, you can see the same thing is happening. The lift is going up, it's now stalling, lift is dropping, drag is going up till we get to around 90 degrees angle of attack. So now this is, let's type in 90 there, we're at 90 degrees angle of attack, so this is like, if this is our wing, it's now just falling straight down. It's just getting drag, no lift, but as I carry on going, the wing is now effectively flying backwards, so the wind's coming from towards the trailing edge, but it's at a positive angle of attack on the trailing edge, and we're generating lift that way. So wings do work backwards. They're not quite as good as when they're working forwards, but they will produce some lift. Great, so let's set this to, say, 20 degrees angle of attack. And the other thing we're interested in terms of modelling things that fly, if this is a wing, it won't always fly that way. So it may start flying with the wind from the side. If you're a plane, you're flying in side slip. So how does the lift vary when you change the azimuth of the wind or the side slip of the wing? So we can do this by varying the azimuth. So the wind is sort of coming from in the plane, and as we swing it round, if we get to 90 degrees, the wind is now coming straight up the side of the wing like that. And so imagine this is a ruler someone's chucked in the classroom, they've kind of thrown it, it's sort of flying at an angle like that, but it's like a really thin wing, so it hasn't really got any wingspan to it at all. It will still produce some lift and quite a lot of drag, and Aerodynamic Objects is happy with that, given the shape of the wing, the angle, the angle of attack, the angle of side slip. The lift model will calculate a reasonable approximation of what the lift would be. So if that really was a ruler flying across the classroom, this would be a fairly decent estimate of what the lift and drag is on there. and we can carry on all the way around, and then we're kind of back to where we started, just going backwards. The other thing which we're interested in here in terms of our lift modelling is it really matters where the lift acts on this wing. So imagine this really was a ruler. If the lift's acting to the front of it, the front will tip up when it's flying. If the lift is acting at the back, it'll tip the other way. So for an aircraft, it makes a big difference where the lift acts. And from a technical perspective, the location of the lift is called the aerodynamic center. If we've got a flat plate wing like this, the aerodynamic center is coincident with the center of pressure, which is a probably easier concept to understand. If you imagine we've got a pressure distribution on this wing, it's kind of where, if you added up all the pressure, where would you put your finger to kind of balance it? So that's where the lift acts. And from wing theory, at low angles of attack, you would expect the aerodynamic center to be around a quarter chord. Let's reduce this down to 10. So at lower angles of attack, the location of the lift is about a quarter of the way back from the leading edge. But if we increase the angle of attack, what you see there is the aerodynamic center position moves back until we get to 90 degrees angle of attack, and now the lift, or what's left of it, is acting at the center of the object. And if we keep on going round and the wing is going backwards, that aerodynamic center moves round to around quarter chord in the other direction. So that's all handled by the lift model. And so what that means is you can make a fairly arbitrary shape like this, fly it at arbitrary angles, and the lift model will correctly predict where the center of lift acts. And that means the dynamics of your object is going to be reasonably correct. One other thing we can look at is what happens to that aerodynamic center when we have a side slip or azimuth. So if I vary this, we can see as we get round to our flying sideways, that aerodynamic center has moved out to there. So it's now roughly a quarter of the way back, or in the chordwise sense this way. And so that's the correct position. So if that was our flying ruler, you would find in practice the lift on that ruler is acting somewhere around here. So it probably would pitch up. If you launched it in space like this, it would probably pitch upwards. Excellent. So we've seen that you can vary the angle of attack by varying the angle of the object relative to the surroundings, or you can vary the orientation of the wind relative to the object. But there's another way of changing the lift, and that's by adding a control surface. So we're going to do that. If we go to the aerodynamics object, what we're going to do is add a control surface component. So control surface, and it's the one with the AO badge on it. And if you notice then, this red box appeared on the back, and what that is now a control surface on our object. And we can set the position of how much chord it takes up. So the maximum you can do is half the chord, or you can reduce it. So we can set the size of the control surface, and that will determine how effective it is. So obviously a larger control surface has more effect than a smaller one. But we also, if we want to see in some graphics so that the humans can see what's going on, if we do add another component, which is control surface graphics, and hit update on that, it'll create a bit of graphics so that it moves with the control surface. So if we put in a control surface deflection and then do update, we can see there we've got a bent trailing edge. Okay, let's see what that does. Reset the control surface to 0. I'm going to, with my uniform flow, I'm going to pull this out as a separate window. If we play that, so we're at 0 geometric angle of attack, the wind's at 0, control surface is 0, nothing happens. Okay, so that's the right answer. So if we now try changing the control surface, so I'm deflecting it down, and there you can see magically the lift is going up. And if I do control surface trailing edge up, that makes the lift go down. Okay, and that's how you control a plane in flight. You're not changing the actual angle of attack, you're changing the relative angle of attack using a control surface, and that's what changes the lift on the surface, and that's what makes a play. That's how you control the plane. The aerodynamic theory of this is reasonably complex, how a control surface works, but the simple way of thinking about it is effectively you're changing the average angle of the surface. So when you deflect something down, if you imagine you joined a line between the trailing edge and the leading edge, it's sort of more at an angle, and that's increasing the effective angle of attack of the surface, and that's producing more lift. So summary, how do wings work then? So the important thing we've seen is that a wing will produce lift when it is set at an angle to the wind. So we can either move the wind, or we can move the wing, or we can act as a control surface, but the main thing is that the lift is proportional to this angle between the plane of the wing and the wind, and that angle is called the angle of attack. Great, so that kind of ends this tutorial. In our next tutorial, we are going to be taking this wing and using it as the fin on a weather vane. So we're going to introduce some dynamics into it. The fin is going to be producing lift, and we're going to use that lift to make our weather vane point into the wind. Look forward to seeing you in the next tutorial.